So let's look at a couple examples here where we can use that definition of continuity at a point to determine whether a function is actually continuous at a point. So the first thing I want to point out is this question here is asking specifically about the point x equals 2. If we look at points not at x equals 2, so any point less than x equals 2, we're going to be looking at this function, and we're not going to have any trouble with continuity with a function that looks like that. A polynomial is going to be continuous because we don't have any trouble putting in points, and the limits are going to exist. And same thing is true for the right branch, everything greater than 2. So the only question here is at the boundary for our piecewise function. So where we change from the top function to the bottom function at x equals 2 is where continuity might come into question. So let's check those conditions. The first condition is that f of c, in this case f of 2, exists. And we can figure out what f of 2 is just by plugging 2 into the bottom one, and I chose the bottom one because that includes x equals 2. So this is going to be 2 cubed plus 1, which is going to be 9. So not only does it exist, we know the value of f of 2. So our first condition for continuity is met. Second condition is that the limit as x approaches 2 of f of x also exists. Well, for this, we're going to need to look at both of our one-sided limits. So let's look at the limit as x approaches 2 from the left. And as we approach 2 from the left, we're going to be looking at values smaller than 2. So we're going to be on this branch right here. And even though we're looking at values slightly smaller than 2, we can plug 2 in because we're getting really close to 2. So direct substitution works here. We plug 2 into this expression. It's going to be 2 squared plus 2 times 2 plus 1, which is 9. And the other one-sided limit, the limit as x approaches 2 from the right of f of x. Now we're looking at values slightly greater than 2. Again, it doesn't matter that it's actually equal to 2 here. That doesn't make a difference as far as the limit goes. We are getting really close to 2 though, so we can plug 2 in here, and we're going to get 2 cubed plus 1, which is 9. So both of our one-sided limits are the same, which means that it does exist, and we know the value is 9. Okay, so our second condition is met. Now, our third condition I actually checked by finding the values of the function and the limit. So the third condition is that what we got in step 1 is equal to what we got in step 2. So the value of the function is equal to the value of the limit, and that is true, which means that this function is continuous at x equals 2. So I want to take this problem and change it just a little bit. And so if we look at it here, we actually know the answer to this. I want to be upfront with this. We know the answer to this because of the problem we just did, but we might be asked a question in a slightly different way. So we might say, okay, we know f of x is continuous. We have this piecewise defined function. So what does k have to be to make it a continuous function? And we know the answer to this because of the last problem. It was exactly the same, except we had a 1 where the k was. So we know that the answer is going to be 1. But let's figure out how we would actually figure that out in this problem. So remember, our left-handed limit and our right-handed limit and the value of the function all have to be the same thing. So in order to figure this out, essentially what we're going to do is we're going to look at the limit as x approaches 2 from the left of f of x, and that's going to be looking at this branch. And if you remember in the last problem, we figured that out just by plugging 2 in for x. So that's going to end up being 9. And the limit as we approach from the right of f of x, which is going to be our bottom branch, we figure that out by plugging 2 in for x. In this case, that's going to be 8 plus k, and those two limits have to be equal to each other. Now, this bottom one here actually does two things for us. Not only does it tell us what the limit as we approach from the right is, but it's also telling us what the value of the function is at that point because it includes x equals 2 here. So this right here is the value of the function at x equals 2, and it's also the value of the right-handed limit at x equals 2. So for this to be continuous, we know these two things have to be equal to each other. So we set them equal and we solve for k. So we get k equals 1. So the idea here is that in order for this function to be continuous at the boundary with our piecewise function, what we do is we take the x value and plug it in for x, and then we set them equal to each other. And by doing that, we're making sure our two one-sided limits are equal, and then also because x is equal to 2 with our right-handed limit, that also gives us the value of the function equal at that point. Just a quick look at a graph for this problem. So in red, we have the branch for when x was less than 2. In blue, we have the branch for when x is greater than 2. And I have a slider here for k, so I can plug in any k value I want. And as I move this slider around, we can see the function moves with me. And so I could do this if I have graphing software like this. I could do this kind of by trial and error and just kind of move this until I get a function that's continuous, and that gives me my k value of 1. So the idea here is we're just trying to figure out what that k value is, and we can evaluate that numerically or algebraically using the ideas with limits that